Now we have Debye-huckel theory of strong electrolytes to discuss. But before this theory, we have already grasped the idea of Arrhenius' theory of electrolytes. Arrhenius introduced that theory for both strong electrolyte and weak electrolyte, but concept was not in good agreement with strong electrolytes because of some wrong assumptions made by Arrhenius. So, to explain the conductivity of strong electrolytes, Debye and Huckel now introducing a new theory, namely Debye-Huckel theory. What are the major concepts of Debye and Huckel? It can be listed like this. All strong electrolytes are completely ionized even then they are in solid state. For example, in NaCl crystal, you have already studied in solid state that there is no sodium atom or chlorine atom. There we have Na plus ions and Cl minus ions. The Cl minus ions form the FCC arrangement and Na plus ion can occupy the octahedral void formed between the Cl minus ions. This concept you have already studied. So, even in solid state, these compounds are or electrolytes, strong electrolytes are completely ionized, but the problem is their mobility. In solid state, they are unable to move from the existing position, or simply they are immobile. Because of this immobility, they are not good conductors of electricity in solid state. But when dissolved in suitable solvent of sufficient dielectric constant, they start to conduct electricity because of their mobility. When these solid electrolytes are dissolved in a solvent, these ions get separated and they become mobile through the solution, so they can conduct electricity. The conductivity of such an electrolyte is dependable on the interionic attraction. That means how cation attract anion, or how anion attract cation, or how these ions can influence each other. If there is a good attraction between the oppositely charged ions even in the solution, their conductivity will be less, and if they are free without having much attraction between them, there will be high conductance can be expected. So, the interionic attraction of electrolytic ions in a solution can be explained using two effects: relaxation effect or asymmetry effect. Asymmetry effect, or second one is electrophoretic effect. We have to see it one by one. First one is relaxation effect. Suppose you have been provided with an electrolytic solution containing positively charged and negatively charged ions. It contains many positive charged ions and many negative charged ions, and they are free to move through the solution. So, under such condition, there may be a formation of electron cloud. Formation of a charged cloud is observed around each ion by oppositely charged ion. But I mean positive charge in solution, each positive charge is surrounded by negative charges in a symmetric manner. As it is a symmetric electronic atmosphere, it will not have any problem on the mobility of such ion to greater extent, and each negative ion is also surrounded by positive ions. So each ion is surrounded by oppositely charged ions in a symmetric way. This is the condition in an electrolyte before applying electric power. So when we apply electric potential for electrolysis, what actually happen? Positively charged electrode, that means anode. Negatively charged electrode means cathode. Positive ion move towards the negatively charged electrode. At the same time, all the negatively charged ions move towards the positive electrode. So by applying electric field, the symmetry of this charge cloud is completely disturbed. Symmetry of the ionic atmosphere is completely disturbed. Then it become like this. Positive charge move towards this end and negative charges move towards this end. They will move in this direction and positive charge in opposite direction. When the symmetry of ionic atmosphere is disturbed, these negative charges definitely attract this positive charge in back direction. So positive charge cannot move as it wishes to. Even if it wishes to move with high speed, because of this backward drag from the negatively charged ionic atmosphere, they will experience some kind of backward pull and their speed will be retarded. This retarding influence of a particular ion on the speed of the oppositely charged ion is called relaxation effect or asymmetry effect. After some time, positive charge again become its symmetric ionic atmosphere. So after getting into asymmetric condition, few times this positive ion has to wait to regain its symmetry. When symmetry is regained, they can move with high speed. This time lag between the asymmetric condition to the symmetric condition is called relaxation time. ഒരിക്കൽ അസിമെട്രിക് അയോണിക് അറ്റ്മോസ്ഫിയർ ജനറേറ്റ് ചെയ്യപ്പെടുന്നതോടുകൂടി അയാൾക്ക് പിറകിൽ നിന്ന് ഒരു അട്രാക്ഷൻ ഫീൽ ചെയ്യുകയും അയാളുടെ വേഗത കുറയുകയും ചെയ്യും. എന്നാൽ അല്പസമയം അയാൾ വെയിറ്റ് ചെയ്താൽ വീണ്ടും അയാൾക്ക് ചുറ്റും ഒരു സിമെട്രിക് അറ്റ്മോസ്ഫിയർ ഡെവലപ്പ് ചെയ്യുന്നതായിട്ട് കാണാം. അപ്പോൾ അയാൾക്ക് വീണ്ടും ഹൈ സ്പീഡിൽ മൂവ് ചെയ്യാം. അപ്പോൾ ഒരിക്കൽ അസിമെട്രി ജനറേറ്റ് ചെയ്ത് റിട്ടാർഡേഷൻ വന്നതിന് ശേഷം തിരിച്ച് സിമെട്രിയിലേക്ക് എത്തുന്നത് വരെയുള്ള സമയത്തിനാണ് നമ്മൾ റിലാക്സേഷൻ ടൈം എന്ന് പറയുന്നത്. അത്രയും സമയം അയാൾക്ക് സ്പീഡ് കുറവായിരിക്കും. റിലാക്സേഷൻ ടൈം കഴിയുന്നത് വരെ അല്ലെങ്കിൽ സിമെട്രി തിരിച്ച് കിട്ടുന്നത് വരെ അയാൾക്ക് സ്പീഡ് കുറവായിരിക്കും. എക്സാമിന് നിങ്ങൾ ഈ രണ്ട് ഡയഗ്രങ്ങളാണ് വരയ്ക്കേണ്ടത്. ഇവിടെ പോസിറ്റീവ് അയോൺ ഈസ് symmetrically surrounded by negative ions, or these negative ions provide a symmetric ionic atmosphere around positive ion, so speed of the ion is not influenced much. But when electric field, positive field and negative field is applied, positive ion move towards negative electrode and negative ion towards the positive electrode. This will create some kind of asymmetry and a backward drag is experienced by the positive ion from the negative ions, which reduces its speed, and this effect of negative ion on the speed of positive ion is called relaxation effect or asymmetry effect. After this asymmetry, again condition of symmetry can be regained but between these two, this positive ion needs to wait for some time. That time is called relaxation time. Till the end of relaxation time, speed of positive ion will be less than the expected one. Now we have to electrophoretic effect. We are considering now electrophoretic effect. This is the picture of asymmetric effect. Okay. In addition to asymmetric effect, the next problem is that positive ion move in one direction and negative ion move in opposite direction. That is okay. Each negative ion is surrounded by definite number of solvent molecules. This solvent is shown here. Each negative ion is surrounded by definite number of negative ions in solution. When this negative ion move towards the left side or positive electrode, along with the negative ion, the surrounding molecule, solvent molecule also move in that direction. So, the flow of ions and solvent takes place towards this direction. But this positive ion needs to flow in opposite direction. That means the positive ion has to flow against the stream. Stream is in this direction, but it has to move against the stream, which also reduces the speed of the cation. This effect of solvent molecules on the mobility of this ion is called electrophoretic effect. If the speed of the ion is retarded by the generation of or formation of an asymmetric ionic atmosphere, that is called asymmetry effect. Along with the asymmetry effect, the anions surrounded by a definite number of water molecules, they are also moving in that direction of negative ion, that make the stream in a direction opposite to that of cation. So cation needs to flow against the stream, which also reduces the speed of cation. That retardation due to the influence of solvent molecule is called electrophoretic effect. These two effects actually reduces the speed of the ion. This is true in the case of anion also. Each anion is surrounded by an ionic atmosphere of positive ion. When electric field is applied, negative ion move in this direction and positive ion in this direction. There also we have the asymmetry effect and electrophoretic effect. So the speed of negative ion can also be reduced. So it is true in the case of cation and anion. So greater the concentration of the solution, greater will be the asymmetric effect and electrophoretic effect. So mobility will be less and conductance will be less. So the conductance increases with decrease in concentration or dilution. When dilution happens, asymmetry effect and electrophoretic effect diminishes and mobility of the ion slowly increases. Fifth point is mobility of the ion in solution is also dependable on frictional force offered by the solvent. That is called viscosity of the solvent. When solvent is a highly viscous one, movement of ion through that viscous medium is difficult, then conductance decreases. By connecting limiting molar conductance, that means the conductance of a solution at infinite dilution and electrophoretic effect, concentration and asymmetry effect. Debye, Huckel and Sagar derived an equation like this: lambda mc equal to, lambda mc means molar conductance at a given concentration equal to lambda m0. It is the molar conductance at infinite dilution minus these parameters. This is the contribution from electrophoretic effect and this is the contribution from asymmetry effect. Electrophoretic effect and asymmetry effect. Here you can see lambda mc, molar conductivity at a concentration C, lambda m0, molar conductance at infinite dilution. D is the dielectric constant of the medium. Eta is the viscosity of the medium. Eta actually represents the coefficient of viscosity. T is the temperature in Kelvin, and C represents molar concentration of the solution. So sum of these two parameters need to be multiplied with root of the concentration and subtracted from the final value. Final value means lambda m0. Then we will get the current lambda m. This can be simply written as these two are two constants a and b, then lambda m equal to lambda m0 minus a plus b into lambda m0 into root c, where a and b are constants for a given solvent and dependable on the viscosity and dielectric constant of the solvent. It is y equal to mx plus c. When we plot a graph between x root c and y is lambda m, we will get a straight line like this for strong electrolyte. But this relation is valid only at lower concentration or at higher dilution. In this region, this relation is valid. In this region, relation is valid. Here, relation is valid, but higher concentration it deviates from the Debye-Huckel equation. So Debye-Huckel equation can be applied only in dilute solutions. At higher concentration, this relation is not valid. Now we have to see the proof for the existence of ionic atmosphere or influence of electric potential and high frequency on the conductance of a solution. Proof for existence of ionic atmosphere. It can be explained using Wien effect and Debye falkenhagen effect. Wien effect and Debye falkenhagen effect. Wien effect is the influence of high electric potential on the conductance. At very high voltages, around 10 raised to 5 volt per centimeter, increase in molar conductivity of electrolyte can be seen. This fact was first observed by Wien, and so this effect is known as Wien effect. For that, in an electrolytic solution, two electrodes are placed and high electric potential of around 10 raised to 5 volt is applied. Under this high voltage, for electrolysis to happen, this kind of a high voltage is not necessary. We have to apply only the potential greater than the theoretical value plus over potential. That is the only expected value. But if we increase the potential up to 10 raised to 5 volt, what actually happens is that the speed of the ion increases to 0.1 meter per second, but relaxation time is only 10 raised to 9 times less than it. And thickness of the ionic atmosphere we have discussed in asymmetry effect is 0.1 nanometer. Speed is 0.1 meter per second. It is 10 raised to 9 times greater. Because of the high speed of the ions, suppose a positive ion, it needs to be surrounded by a negative ion. and negative ion form an ionic atmosphere around the positive ion in a symmetric manner. This was the condition we have discussed in asymmetric effect. But when this positive ion move with high speed, in order to form an ionic atmosphere, a short time is required to order all these ions in a symmetrical fashion. Some time is required. That much of time this positive ion should be stationary to form this anionic cloud. But under high potential, this cation cannot exist in a stationary mode. It will move with high speed. So the negative ion can never form a symmetrical ionic atmosphere around the cation, or cation cannot form an ionic atmosphere around the anion. Actually, this asymmetric effect and resulting electrophoretic effect completely disappear in this condition, and solution conducts to high values, or lambda m will be very high even at high concentration. Normally the lambda m will be high only at low concentration and infinite dilution, but we can expect the lambda m infinity value even at high concentration if we are ready to apply high electric potential, where speed of the ion is very high, speed of positive ion and cation is very high, so that ion cannot be surrounded effectively by the oppositely charged ions to make an ionic atmosphere, which then form a symmetric effect and electrophoretic effect. So the possibility of both the effects, asymmetric and electrophoretic, are completely lost. An ion is fully free to move through the solution, and so they conduct electricity. So it is one of the proof for the existence of ionic atmosphere in normal concentration. So at normal concentration and normal potential, under normal potential, there will be ionic atmosphere. So that under that conditions of lower potential, conductance vary with dilution. But at higher potential, conductance is not dependable on the dilution process. Second one is Debye falkenhagen effect. Debye falkenhagen effect. It is the influence of high frequency AC. Wien effect is the influence of high electric potential. It is the influence of high frequency of AC on the conductance. How the conductance of a solution or electrolyte vary when high frequency AC is applied. When very high frequency AC current is used, of the order of 3 to 5 megahertz, increase in molar conduction of electrolyte can be seen. This fact is known as Debye falkenhagen effect. How it can be explained? When very high frequency of AC is used, around 3 to 5 megahertz, the time for oscillation is less than the time of formation of ionic atmosphere. As we have seen, for the formation of ionic atmosphere, this ion needs to be stand for some time to form this ionic atmosphere. But under high frequency AC, the oscillation time of the ion will be very high, so that negative ion or oppositely charged ion cannot form ionic atmosphere around it. So under high frequency AC also, asymmetric effect and electrophoretic effect actually disappear. So the ion can never surround the oppositely charged ion to create asymmetric effect or electrophoretic effect, and in the absence of electrophoretic and asymmetric effect, solution exhibit very high conductance at high frequency AC. This is called Debye falkenhagen effect. So in exams you may be asked for Wien effect and Debye falkenhagen effect. Wien effect actually represent influence of high electric potential on the conductance of solutions, and Debye falkenhagen effect giving the influence of high frequency AC on the conductance of solution. Both effect clear out the absence of symmetric effect and electrophoretic effect under these two conditions, and so the electrolyte conduct electricity to greater extent, or they exhibit high conductance under high potential and high AC frequency. But under normal potential and AC frequency, speed of the ion will be somewhat less, and the oppositely charged ions can form an electron cloud around it. Then on applying electric potential, definitely there will be asymmetric effect followed by electrophoretic effect, which retard the speed of ion. All these conditions will be ceased at higher potential and higher AC frequency. So with this, these two effects, Wien effect and Debye falkenhagen effect, can be considered as the proof for the existence of ionic atmosphere in normal potential and normal concentration. In exam, you may be asked different kinds of questions from this topic. You have to be equipped to answer such questions. Thank you.